Welcome back. This is Dynamics Video 2. Alright, in this one we're going to focus on multi-object systems. So we got a system, but there's more than one object inside of it. We haven't really looked at this too much yet. So, if there's an object of interest interacting with several other objects, the net force is the vector sum of all of the individual forces. Alright, so here's a classic example. I have two objects connected with a string. I have an outside force, F, that's going to act on them. And this F will accelerate the system. And, there's several things that could potentially happen. So, the first thing we need to do is we need to make a free body diagram for each object. So whenever you have multiple object systems, make a diagram for each object. So this first one, we have our force that's pulling on it. We have a normal force. We have a gravitational force. And we got two forces actually pulling back. We have this tension force because of the string, but we also have some kinetic friction because there's two surfaces in contact. So we got two forces pulling back. For the other object,
Interruption. Soccer players in the cafeteria need to knock off the horseplay. Have a seat.
so for this other one, we've got tension, that's pulling it, normal force and gravity force, and then we've got some kinetic friction that is opposing it. Alright, now that we've labeled all of our forces, we need to start studying them on each axis. So, for this box, if I were to take a look at the sum of forces on the y-axis, I've got a normal force minus a gravity force, and it's in equilibrium on the y-axis. So that means then that the normal force would equal the gravity, which is mg, which, for this case, the normal force then m is 5m. So we got that. Then I can take a look at the forces on the x-axis. I have tension minus kinetic friction, and this time it is not in equilibrium, so it will equal ma. So then that means that tension, now remember friction is the coefficient times the normal force, and mass is 5m. And I just found out what the normal force was in this line right here. So and what this does is it gives me one equation. I'm assuming that we know what the mass is, we know g, we probably know the coefficient of friction. However, we do not know the acceleration or the tension force. So we got two unknowns. We need a second object. So I'm going to do the same exact thing to this other box. So along the y-axis we have equilibrium. So that means that the normal force equals mg. So the normal force really is 2mg. On the y-axis, I have the pulling force minus tension minus friction, and it's not in equilibrium. It said in the problem it's accelerating, so it's going to equal ma. So then, I know what the normal force is. Should have put a 2 in front of there. This gives me a second equation. So, let's say I wanted to calculate the tension force. What I would do is I would solve both of those equations for acceleration. That way I can set them equal to each other. So the first equation then would look like it'd be ft minus mu 5, not f. And then the second equation I could set those two equal to each other. I'll spare you the algebra, but basically what it comes down to is that the tension force would equal 5/7 of the pulling force. So I'll leave it to you to work out that algebra. It's really not too bad. A lot of things cancel out, especially the masses, the coefficients of friction. A lot of that stuff cancels out. Here's another classic example. It's a modified Atwoods machine. So here I have two objects connected by a string over a pulley. We assume the pulley is massless and frictionless. Once again, we need to make a free body diagram for each object. So here M1, there's some tension pulling up, gravity pulling down, and the same thing for M2. In this one, let's assume M2 is more massive than M1, and then I think you would see that the system will accelerate. Now M1 is going to accelerate in a positive direction. M2 is going to accelerate in a negative direction, and that's very important. So for M1, the sum of forces on the y-axis would look like that. So in other words, tension minus, this would be M1G equals M1A. That gives me one equation. For the second one, what I'd get is the tension minus M2G equals negative M2A. Again, it's negative because M2 will be going down, so it's going to accelerate in a negative direction. So in this one, let's say I want to know what is the acceleration. In that case, I would solve both of these equations for tension force to get rid of it. So I would have I would set those equal to each other. And again, what you would come up with is the acceleration equals M2 minus M1 times G the product of their masses on the bottom. Again, I'll leave it up to you to work out that algebra. It's not hard. It's very, very simple. So, forces that forces that systems exert on each other are due to the interaction between the objects inside the system. So if the interacting objects are parts of the same system, there will be no change in the center of mass velocity of that system. So what that means, if this Atwoods machine, this pulley system, if it were like in a spaceship traveling through space, the fact that it's operating would not affect the motion of the spaceship. That's basically what that's meaning right there. All right, this was a shorter unit. This concludes the second video.